Here we are again at the edge of the solar system, where the Kuiper Belt, that massive ring of frozen debris beyond Neptune, continues to surprise us. But this time we won't be talking about the individual worlds that populate it. This time we'll look at the belt itself as an overall structure, and we'll discover it's even more bizarre than you imagined. It's a cosmic archive, a recorder of catastrophes, a structure that bends and twists through space. It's a place where most of the matter has vanished into thin air. Let's go. Just a moment, guys. Only 13% of subscribers know when we publish new videos. Make sure you subscribe and turn on the notification bell, because without it, you'll miss formats and documentaries you won't find anywhere else. The classical Kuiper Belt has two distinctly different populations. The area between 42 and 45 astronomical units, or 3.9 to 4.2 billion miles, or 6.3 to 6.7 billion kilometers from the Sun, is called the classical Kuiper Belt. And this region is home to two distinctly different object populations. The first is known as the cold population, and these objects have nearly circular orbits that are generally inclined with respect to the ecliptic by less than 10 degrees. The second population is known as the hot population and consists of objects that have orbits inclined by as much as 30 degrees or sometimes more. Note that the words cold and hot don't refer to the relative temperature of the two populations, but to the differences in their orbital velocities, following an analogy with how gas particles behave when they're heated up. The plane of the belt is warped. Unlike the main asteroid belt, which is relatively flat, the Kuiper Belt has a shape more like a donut because its objects are distributed across a wide range of orbital inclinations. In 2017, however, Catherine Volk and Renu Malthora of the University of Arizona discovered something baffling. It seems the average plane of the Kuiper Belt is much more tilted in the outer regions. By analyzing the orbital inclinations of over 600 objects, they found that up to 50 astronomical units, or 4.6 billion miles, or 7.5 billion kilometers, everything is normal, with the belt lying flat and tilted by just 1.8 degrees. But beyond that distance, between 50 and 80 astronomical units, or 4.6 to 7.4 billion miles, or 7.5 to 12 billion kilometers, the plane progressively tilts until it deviates by more than 9 degrees from what's expected. The probability that it's a statistical artifact? Only 1 or 2%. It's real. Something is warping the belt. There could be an object with a mass similar to Mars orbiting at about 60 astronomical units, 5.6 billion miles or 9 billion kilometers, whose gravity has slowly bent the orbital plane over billions of years. Or it could have been the close passage of a star during the first few million years of the solar system. But there's more. This warp isn't static. The plane of the belt precesses slowly with a period of 1.9 million years, as if the entire structure is breathing. We've even weighed it. How do you weigh something that's over 3.7 billion miles or 6 billion kilometers away and then extends for billions of miles more? Andrea Di Ruscio of La Sapienza University in Rome and his team found an ingenious method. They used Saturn as a cosmic scale. During the 13 years of the Cassini mission, the probe was tracked with incredible precision through radio signals exchanged for 6 hours a day with the Deep Space Network. By analyzing the Doppler effect and signal delays, scientists managed to determine Saturn's position with an accuracy of just 1 meter or 3.3 feet, creating one of the most precise planetary ephemeris tables ever produced. At that point, they compared Saturn's actual orbit with the theoretically predicted one, and found tiny perturbations caused by the cumulative gravitational pull of the belt. By analyzing the perturbations caused by the 9 largest known Kuiper Belt objects, it was possible to calculate that its total mass is 1/16 that of Earth. Really very little, barely 5 times the mass of our Moon, a fact that immediately connects to what follows. Most of its mass has disappeared. Here's one of the deepest and most baffling mysteries of the Kuiper Belt. Where the hell did all the stuff go? Models of the solar system formation tell us that in the region beyond Neptune there should have been a massive disk of planetesimals, the building blocks from which planets form. Estimates speak of 20, 30, maybe 50 Earth masses of material. It was a dense, populated region full of objects colliding and accumulating onto each other. But when astronomers did the math on the current mass of the Kuiper Belt, they found that all the matter out there doesn't even amount to 1/16th of Earth's mass. And it's not a margin of observational uncertainty. It's a cosmic void screaming for explanations. Where have those 20 Earth masses of ice and rock gone? Were they ejected from the solar system? Did they collapse towards the sun? Did they disintegrate into dust that was blown away by the solar wind? The answer, as often happens in astrophysics, trails off into a trickle of hypotheses, though the main suspect remains Neptune, which in the first few million years after formation migrated outward, dispersing like a cosmic bulldozer all the material in its path. But there's another mechanism that continues eroding the belt even today: the collisional cascade. Objects in the belt collide with each other, fragmenting into ever smaller pieces. These fragments are then blown out of the solar system by solar radiation pressure and the solar wind. It's a slow but inexorable process. The Kuiper Belt is slowly self-destructing, grinding its members into dust that's then dispersed into space. In a few billion years, when the sun becomes a red giant, the Kuiper Belt might be completely gone, the last whisper of what was once a massive and imposing structure. The belt we see today is just the shadow, the pale ghost of what once existed. And with this, we connect nicely to the next topic. Hey Curious Squad, before moving on, be sure to subscribe to our channel, clicking on the notification bell, and leave us a thumbs up so you don't miss out on our daily videos. Other stars have one too. For decades, astronomers wondered whether our Kuiper Belt was unique or if every planetary system had its own donut of frozen debris. The answer came thanks to space telescopes and infrared observations. Kuiper Belts are common, very common. They're practically the norm for mature planetary system. But here's the interesting part. Comparing our belt with those of others, we've discovered that ours is strangely small and poor in material. Around stars like Vega, astronomers have identified enormous disks of dust and debris extending for hundreds of astronomical units. The Fomalhaut system shows multiple rings of material, some perfectly circular, others eccentric and misaligned. Epsilon Eridani, a sun-like star just 10.5 light-years from us, has a massive debris disk that shines brightly in the infrared. And then there's HR 8799, where the Hubble telescope captured direct images of a vast ring of dust dotted with giant planets. Comparing these systems with ours, the Kuiper Belt appears like the poor decimated version of what should be a residual protoplanetary disk. By 2006, astronomers had cataloged debris disks around 9 stars, and since then the number has grown exponentially. What emerges is that these disks seem to divide into 2 categories: wide belts with radii greater than 50 astronomical units, 4.6 billion miles or 7.5 billion kilometers, and narrow belts like ours, with radii between 20 and 30 astronomical units, 1.9 to 2.8 billion miles or 3 to 4.5 billion kilometers, and relatively sharp boundaries. But why this difference? Computer simulations suggest that when the solar system was young, our Kuiper Belt might have been much more similar to the narrow, dense disks we see around young stars. Over time, the gravitational influence of the giant planets, internal collisions, and probably catastrophic events like Neptune's migration have eroded and impoverished the belt, leaving us with the remnants we see today. It's like we're looking at the ruins of a once far more grandiose structure. Is it just a matter of age? Vega, for example, is much younger than the Sun. We don't know yet, though obviously this is the main hypothesis. The first time we went there, it was empty. In 1983, Pioneer 10, launched 11 years earlier to study Jupiter, is traveling toward the unknown. On June 13th, it passes Neptune's orbit, becoming the first human-made object to push beyond the orbit of the last planet in the solar system. It's entering the Kuiper Belt, but there's a small detail. Nobody knows it, because in 1983, the Kuiper Belt didn't exist, not officially at least. Oh sure, there had been speculations. Kenneth Edgeworth in the 1940s, Gerard Kuiper in the 1950s, Julio Fernandez in the 1980s had all theorized the existence of a population of icy objects beyond Neptune. But they were theories, hypotheses. No one had ever seen a single object out there, except Pluto, discovered in 1930 and considered at the time the ninth planet rather than the largest member of an unknown population. So when Pioneer 10 crossed that region, it was crossing a space that everyone thought was practically empty. Only 9 years later, in 1992, David Jewett and Jane Liu spotted 1992 QB1, now called Albion, the first confirmed trans-Neptunian object after Pluto and Charon. That discovery opened the floodgates. In the following months and years, discoveries multiplied. Today, we know of over 2,000 objects in the Kuiper Belt, and new ones are discovered every year. Is it still alive or just a graveyard? One of the most fascinating questions about the Kuiper Belt concerns its current status. Is it a geologically and dynamically living structure, continuing to produce new objects and shape itself? Or is it simply a cosmic graveyard, a static deposit of frozen debris slowly waiting to disintegrate? The answer, as often happens, is a bit of both, but with unexpected surprises. On one hand, the Kuiper Belt is clearly eroding. Collisions between objects continue to occur, though much more rarely than in the violent past of the solar system. Each collision produces fragments. Some become smaller belt objects, others become comets that are pushed towards the inner solar system by Neptune's gravity, and still others are ground into dust that the solar wind sweeps away. It's a slow process of self-consumption. The total mass of the belt is decreasing, microscopically, year after year. But to say the belt is dead would be profoundly wrong. Recent discoveries have revealed that many objects in the belt are geologically active, at least seasonally. Makemake emits methane into space. Haumea has an impossible ring system that shouldn't exist according to classical physics. Quaoar shows signs of crystalline water ice on its surface, which can only exist if it's been rejuvenated by recent geological processes. These aren't dead bodies. They're worlds that continue to evolve, to change, to respond to the forces acting on them. We can say that those far-flung regions are in a twilight era where geological and collisional activity continues, but increasingly rarely, increasingly weakly. In a few billion years, perhaps the belt will truly be dead, just a pile of debris scattered in stable orbits that will never change again. But for now, it's still alive. Barely, weakly, but alive. It's given moons to the planets. In the continuous dispersal of its members throughout every zone of the solar system, the Kuiper Belt has also managed to donate some of its finest pieces to the outer planets. The most striking case is Triton, Neptune's largest moon, with a diameter of 1,680 miles or 2,700 kilometers. Triton is the seventh largest satellite in the solar system, even bigger than Pluto. But there's something deeply wrong with Triton. It orbits Neptune backward. While all the other large moons in the solar system orbit in the same direction as their planet's rotation, prograde orbits, Triton orbits in the opposite direction, retrograde orbit. This is a clear sign that Triton didn't form together with Neptune. It was captured. And where was it captured from? Almost certainly from the Kuiper Belt. Triton has a density, surface composition, and geological properties incredibly similar to those of Pluto. It has nitrogen, methane, and carbon monoxide ices on its surface. It has active geysers that shoot plumes of liquid nitrogen into the tenuous atmosphere. It has a very high albedo, similar to that of the large Kuiper Belt objects. Every clue points in the same direction. Triton was a large Kuiper Belt object, perhaps part of a binary system like Pluto-Charon that passed too close to Neptune and was gravitationally captured. The same might have happened with Phoebe, a moon of Saturn discovered in 1899. Phoebe is also retrograde and moves in a highly inclined orbit far from the planet. Close-up images from the Cassini probe in 2004 revealed that Phoebe has a composition rich in water ice and dark organic materials, exactly what you'd expect from a Kuiper Belt object. It's likely that Phoebe, like Triton, was captured by Saturn during the early chaotic phases of the solar system. And it doesn't end there. Practically all the irregular satellites of the giant planets, those small moons that orbit on strange inclined paths very far from their parent planets, could be objects captured from the Kuiper Belt or the scattered disk. Jupiter has dozens. Saturn has just as many. Uranus and Neptune have their collections. They're like gravitational trophies, captured memories of close encounters in the solar system's past. In a sense, the Kuiper Belt has left its mark on the entire solar system. Every time we look at Triton or Phoebe, we're looking at pieces of the Kuiper Belt that took an epic journey and ended up in orbit around the gas giants. They're frozen ambassadors from that remote realm, living witnesses to the violent, dynamical history of the solar system. Binary systems are either super tight or super wide. Bizarre fact, binaries in the belt exist only in two extreme configurations, either incredibly close, almost touching, or separated by enormous distances. Intermediate separations are strangely rare. In the cold, classical belt, 30% of objects are binaries, a very high frequency. But many are ultra-wide with separations of tens of thousands of miles, while others are contact binaries like Arikoth. The System 2001 QW322 has components separated by 65,000 miles, or 105,000 kilometers, orbiting at 6.7 miles per hour, or 3 meters per second. They should be destroyed in a few million years, yet they've existed for billions. They are fossils from an era when the belt was dense and velocities were low. On the other side, Arikoth is a contact binary, two lobes gently touching, fused at speeds of 2.2 miles per hour, 1 meter per second. Why are intermediate separations missing? Simulations show they're unstable. They evolved toward one of the two extreme configurations, either merger or ultra-wide separation. The man who named it didn't believe in it. The final irony, Gerard Kuiper, after whom the belt is named, didn't believe it existed. In 1951, he published a paper theorizing a belt beyond Neptune, but concluded it had already dispersed and no longer existed. His logic was based on a reasonable assumption that Pluto was as big as Earth. With such a massive Pluto, gravity would have cleared the region, ejecting all objects toward the Oort cloud. Only in 1978, with the discovery of Charon, did we discover that Pluto was tiny, 0.2% of Earth's mass. The belt exists precisely because Pluto is small, but Kuiper couldn't have known. He did the right calculation with the wrong numbers. Kenneth Edgeworth had made more accurate predictions in the 1940s, and some prefer to call it the Edgeworth-Kuiper Belt. But Kuiper's name prevailed because he was more famous, even though his prediction was that the belt didn't exist. So today, yet another oddity. We're talking about the Kuiper Belt, named after a man who thought it didn't exist. And it's not the only one, since in these 3 videos we've managed to tell you about more than 40. Okay guys, what's the fact that surprised you the most? Let us know in the comments, and to learn more about the Kuiper Belt, check out the videos we've dedicated to it on the end screens.